Now, question 1 says that calculate the eigenvalues, right? And we've been able to do that. Now, so far we've gotten the value, we've obtained eigenvalues, right? Our first eigenvalue, lambda 1 is equals to -2, lambda 2 is equals to -2, lambda 3 is equals to what? 4. Now, what it means is that each eigenvalue has their corresponding eigenvector. Now, the question is, this eigenvector is represented by a column matrix. Now, given matrix was 3 by 3 matrix, right? Meaning the eigenvector will be a 3 by 3 matrix, but it's going to be a single column matrix. Likewise, lambda 2, meaning the second value of eigenvector, eigenvalue, meaning the second number of eigenvalue, and the third number of eigenvalue. Now, let's see how it works. This is still equation 1. You know, earlier I said you are using equation 1. From equation 1, we've gotten eigenvalues. You know, it was equation 1 we used to get our eigenvalues, right? Now, still the same equation 1. We are going to use it to solve what? Eigenvector. Eigenvector. Now, in this case, V is your eigenvector. V is your what? Eigenvector. Now, let's represent V being a column matrix. Let's represent V as a column matrix. Let's say x1, x2, and what? x3. Meaning that for lambda 1, we have the corresponding value of V. For lambda 2, it will have the corresponding value of V. For lambda 3, it will have the corresponding value of what? V. So that's what we are saying. But in this case, recall, when you subtracted lambda multiplied by the identity matrix from this given matrix, what do you have? Check. What was the matrix? Right? When you subtracted it, what was the matrix? Like 1 minus lambda, 1 minus lambda, minus 3, plus 3, 3, minus 5 minus lambda, plus 3, 6, minus 6, 4 minus lambda. This guy, this is it here. You know, we said we are using equation 1. This same equation 1 to get eigenvector. So from this equation 1, I'm replicating each parameters. So for this guy, this is it, right? Then we've said we've represented our V, which is the eigenvector that we are interested in, as this guy. So in place of this V, this is what I have. I have what? X1, X2. I have x1, x2, and what? x3. Equate that to what? 0. So let's say you have a column matrix of 0, 2, meaning 0, 0, 0. Any questions so far? Right. Equation 1. This is still it. That's what we are doing. Now, from here, meaning generally, for lambda 1, this is what you are going to use. For lambda 2, this is what you are going to use. For lambda 3, this is what you are going to use to get each eigenvector of each lambdas. Meaning, recall, you know, the eigenvector, the eigenvalue of 1 is equals to the eigenvalue of 2, which is equals to what? -2. Right? Now, what you are going to do here is that substitute -2 into this guy. Substitute what? -2 into this 3 by 3 matrix. So what do you have? You have that 1 minus -2, that's what? 3. You have -3, 3, 5 minus 2, meaning -5 plus 2. -5 plus 2, and that becomes what? -3. This is what? 4. This is what? 3. Then lastly, we have 6, -6. And what do you have? 6. This is where lambda is equals to -2, right? Now from here, introduce this guy. This is x1, this is x2, this is x3, equals to what? 0, 0, 0. Now from here, what we mean by eigenvector is that we want to know, you know, initially we've represented our eigenvector to be what? X1, X2, X3. Meaning at the end of the day, Any value I have for x1, x2, x3 becomes my what? Eigenvector. So what we are doing here is that we want to solve x1, x2, x3. x1, x2, x3. Now, it is left to you. You know, this is a system of linear equation. This is equation 1. This guy, this is equation 1. This is what? Equation 2. This is equation 3. And so far, we've seen that under linear algebra, you have different methods to solve your system of linear equation. Right? We have the Cramer's rule. You have the Gaussian elimination method. Right? You have Cramer's rule. You have Gaussian elimination method. So in this case, to solve x1, x2, x3, I'll use Gaussian elimination method. I'm going to use what? Gaussian elimination method. And by Gaussian elimination method, you're given matrix, write it in an argumented form. The argumented form of this guy, this is what we have. You know, from here, this equation 1, you can decide to work with this. Right? Are we together? You can decide to work with this, or better still, just divide all 2 by negative 3. You know, from equation 1, 3 is common. You can divide all 2 by what? By 3. Equation 2, 3 is common. You can divide all 2 by what? 3. Equation 3, 6 is common. You can divide all 2 by what? 6. It doesn't mean that we can't continue like this, but to make our work easier, so let's have a lesser number. So let's divide all 2 by 3, 3, and 6. So doing that, what it means is that I have 1, negative 1, 1, 1, negative 1, 1, 1, negative 1, 1. Then this is what? X1. Sorry. This is 0, 0, 0. This is Gaussian elimination method. We are implementing what? Gaussian elimination method. And we said, write in what? Argumented form of matrix. So this is the argumented form. Now, from here, you know, the idea, I've made videos on that already. Argumented form. Yeah, argumented form. You know, I've made videos on that already. You can check my video on Gaussian elimination method or Gauss-Jordan elimination method. The idea behind Gaussian elimination method and Gauss-Jordan is that, given a matrix, I will represent that matrix in an argumented form. Identify your pivot. Generally, your pivot is this guy. So what it means is that any number that you have here, any number, the first number in your row, that's your pivot. The first number in your row, that's your pivot. The first non-zero leading entry. So we are saying that for this matrix, 1 is our pivot. Now, the task of your pivot is that the number under your pivot must be 0. The number under your pivot must be what? 0. So what it means is that, observe, 1 is under my pivot, right? Another one is under my pivot. And this one belongs to what? Row 2. This one belongs to what? Row 3. So if this one is changing to 0, because we said the standard is that this is my pivot, the number under my pivot must be what? 0. So if this guy is changing to 0 and it is in row 2, meaning row 2 is changing all 2. Row 2 is changing all 2. Likewise, row 3 is changing all 2. Now write row 2, row 3. What this means is that you are going to have your manipulation. Your manipulation in the sense that you want any possible way this one can change to 0. That's what you are doing. Any possible way this guy can change to 0. And you are making use of your pivot. If you watch the video on Gaussian elimination method, you understand better. If you watch Gaussian elimination method, Gauss-Jordan, you understand better. So now, your new row 2 from here is row 1 minus what? Row 2. Then your new row 3 is also row 1 minus what? Row 3. Now, row 2 and row 3 is changing, whereas row 1 remain constant. Now, write your new argumented form of matrix, writing the one that won't change, which is row 1. So this is what we have. This is 1 minus 1, 1, 0, right? Then, implementing this my manipulation to row 2, that becomes what? 1 minus 1, 0. Negative 1 minus 1, meaning negative 1 plus 1. Negative 1 minus 1, meaning negative 1 plus 1. That's 0. 1 minus 1, 0. 0 minus 0, 0. 1 minus 1, 0. Negative 1 minus minus 1, meaning negative 1 plus 1. That's what? 0. 1 minus 1, 0. 0 minus 0, 0. Right? Meaning this is your new row 1, this is your new row 2, and this is your what? New row 3. Now, let me say this from here. From here, there's what we call free variable. You know what I'm saying? There's what we call what? Free variable. The idea of free variable is that, looking at this matrix, expected, following Gaussian elimination method, I'm going to get the value of x, the value of y, and the value of z. Right? Now, in this case, you observe that, of the row that will give me x, this is it, right? The row that will give me y, this is it. And the row that will give me z, this is it. But you observe something. The row that will give us y and z is already 0. I get my point. The row that will give us y and z is already 0. Meaning it becomes your free variable. It becomes your what? Free variable. The idea of free variable is that, x, you still get x. Since the row of x, you have values there. Meaning x will still be equal to something. Right? Meaning your x now will now be expressed in terms of the free variable. Now, what is the free variable?
0.
What does this free variable occur? And what value are we going to get in row 2 and row 3? What value out of x, y, z?
X, okay. We are going to get y and z.
Good. We are going to get what? Y and z. Meaning y and z is our free variable. What it means is that x, which is not the free variable, will be expressed in terms of the free variable. Meaning x is expressed in terms of y and z. You get the logic? Because if you do type of solution in linear algebra, you see all these things there. For type of solution, we have ring solution, many solution, and no solution. So this is where all this idea is coming from. Just so that by the time you solve, let's say you are given a normal Gaussian elimination method, and at the end you got something like this. Just have it in mind that the rows you have 0 is called free variable. This guy is called free variable. The idea of free variable is that you can do an assumption that let y to be this, let z to be this. Right? But you see that later on in Gaussian elimination method itself, you see that. But from here, you already have the idea that x is expressed in terms of what? Y and z. For row 1, what do we have? X minus y plus z is equals to 0. I get what I'm saying. But the idea, from here we said row 1, we have x minus y plus z is equals to 0. Expected. I need to get the value of x, y, z. But in this case, I have zeros all true. I also have zeros all true. What does it mean? Free variable. By free variable, x is expressed in terms of this free variable, meaning y and z. So by the time you do that here, what are you going to have?
0, 0.
You don't get the message. When we say something is expressed in terms of the other, meaning you are making down the subject of the formula. Now do that here. That will be what? X is equals to exactly. Say this is equation 1. Then equation 2 becomes what? X is equals to y minus z. Call this equation 2. Call this what? Equation 2. Meaning that, initially, I want to get what? X, y, z. Using this guy, x equals to y minus z. You get x, y, z. You get what? X, y, z. Meaning, depending on the assumption here, x is equals to y minus z, right? Earlier we said our eigenvector v represented our eigenvector. Our eigenvector v, we've represented it as what? X1, x2, x3. I get what I'm saying. We've represented it as what? X1, x2, x3. Now, from this interpretation, from what I have here, what it means is that x1 is equals to what? From this interpretation, what it means is that I want to know the value of x1, question mark, the value of x2, question mark, the value of x3, question mark. From what I've gotten here, to get x1 now, what does it mean? x2 minus x3. x2 minus what? x3. Why is it x2 minus x3? Because this guy, this is row x, this is row y, this is row z. x1, this x1, this is it, equals to y x2, this is it, minus z x3, this is it, right? Now take note that x2 is still the same thing as what? X2. x3 is still the same thing as what? X3. x2 is still the same thing as what? X2. x3 is still the same thing as what? X3. So what you are saying is that in conclusion, the value of my eigenvector, I've represented it as x1, x2, x3. Meaning, what's my x1 now from this interpretation? X2 minus what? X3. What's my x2? X2. What's my x3? X3. Now, let's represent it in the column matrix. We represented it with a column matrix, which is this now, right? Now, let's represent it back in a column matrix. So, this is what I'll be having. X2 minus x3, x2, x3. Any question on this? And from here, this is your final answer. But you can go further by saying that this guy, you want to have it in this format. Can still be written as x2 0 plus negative x3 x2 0 and what? X3. Is that correct? Yeah. From here, this guy, this is still it. This is my eigenvector here. This is still it here. What we just did, instead of getting one column matrix, you are now getting two column matrix. Because S2 plus this will still give us this. Right? What we did is that from here, you are done. But you can go a bit further by saying that this guy, you want to have it in a two column matrix. And this is the representation. This guy is equivalent to this. By the time you open up your bracket, S2 minus this is it. X2 plus this is it. 0 plus this is it. So that's it. Now from here, let's say that X2 is equals to 1, X3 is equals to 1, and X1 is equals to 1. This is my eigenvector in terms of variable, right? But numerically, let me write my eigenvector. So I have that my eigenvector V is equals to what? My eigenvector will now be what? What's my x2? 1. What's my x2 again? Still 1. 0 plus what's my x3? Negative 1. What's my x2? Okay, this is 0. And lastly, what do I have? 1. So this is it. Meaning numerically, this is your eigenvector. But by variable, this is your eigenvector. Up to this level, you are correct. This level, you are correct. This level, you are correct. Whichever level you stop, you are correct. So this is your eigenvector. This is your eigenvector. When lambda is equals to what? Negative 2. When lambda is equals to negative 2. Now, try yourself. When lambda is equals to 4. When lambda is equals to 4. When lambda is equals to negative 2, right? This is what we got. So just try solve when lambda is equals to 4 and get your answer. Nothing is changing. So drop your answer in the comment section. All right.